Okay, let's start. So good afternoon, everyone. My apologies for the little delay. We were waiting for load shedding to kick in, but it hasn't kicked in yet. But okay, we will start nevertheless. My name is Francesco Petruccione. I'm at the moment the interim director of NITheCS, the National Institute for Theoretical and Computational Sciences. And this evening, it's a pleasure to introduce to you Dr. Mesias Alfeus. Mesias is a senior lecturer at the University of Stellenbosch, but he started his academic career in Namibia, where he studied mathematics. Yeah, and then he moved to Stellenbosch for his honors and masters. If I remember correctly, you correct me if I forgot. Yeah, did his PhD in Australia, came back to South Africa over a few stations, and is now a senior lecturer in the Department of Statistics and Accounting. Yeah. So I'm very grateful to Mesias for his talk, because you need to know, and I digress a little bit because I see a few faces that don't usually come to this colloquium. Yeah? NITheCS is in charge of promoting mainly basic sciences and surroundings, which means that it supports theoretical physics, astrophysics, mathematics, statistics, data science, but also the quantitative and computational aspects of biology, finance, and space physics and climate change modeling. Yeah? So it's quite a mixed bag. And the meaning of this colloquium is essentially to promote and dissipate information of the 8 disciplines to the other 8 disciplines, 7 disciplines. Yeah? And we try to keep the colloquium a little bit more general, so that every discipline can profit a little bit. Yeah? And I'm very grateful to Mesias, because he kickstarts our quantitative finance colloquium series, if you want to call it this way. Yeah. So Mesias, people are here to listen to you, certainly not to me. Yeah. So please, if you want to start with your presentation, you're most and welcome. Thank you very much.
Thank you very much, Francesco and NITheCS, for the wonderful invitation to come and speak to you about the current research that you are currently doing. And today I'm going to talk to you about a gentle quantitative modeling approach for the rough crude oil prices. I call it gentle because already we see that the prices for the crude oil are very rough. And this will come to light in a minute. Like Francesco said, I am from the Department of Statistics and Actuarial Science. I'm within the discipline of financial risk management. And first of all, before I continue, I just want to thank you all for coming to my talk. And I'll keep the mathematics relatively simple so that we can all journey together through this research that you are doing. Well, this is joint work with Associate Professor Christina Nictopoulos from University of Technology in Sydney, Australia, and Professor Ludger Overbeck, who is from the University of Gießen in Germany. And Christina, I used to work for her as an associate researcher at University.
Okay, it looks like now they're getting load shedding. Let's just wait for a couple of minutes and they'll be back just now, I assume. Okay, looks like they're coming back.
Okay, I was saying, I think, can we proceed? You can. Okay. I was a research associate for Professor Christina Niktopoulos when I was doing my PhD in the University of Technology in Sydney. And Professor Ludger Overbeck, we met when he came to Sydney, Australia for his sabbatical leave in 2017. And we sat down and then we discussed a sort of research idea with Professor Ludger Overbeck. And we came with a paper which was published in Journal Futures Market. And it was one of the paper which is close to my heart, also about rough volatility. And yes, so the title of the talk is not exactly the same as the title of the paper that I'm going to talk today, simply because we wanted to make it a bit more attractive. And the formal title of the paper is called The Dynamic Roughness in the Term Structure of Oil Market Volatility. And by saying oil market, we simply mean the crude oil. And the full paper is available here on Social Science Research Network, or SSRN, and it can be found here. And I will share the slide with Francesco so that he can share with the audience that are interested. The agenda of my talk, I'm going to take you through the background of our modeling and the motivation behind, and I'll discuss the rough forward models, and which means now you are departing from the classical modeling approach. Now there are no closed form solutions. You have to use probably the characteristic functions, or what we call the Fourier-based methods, in order to price derivatives. And that also come to light later. And we also talk about the empirical result. It's more of an empirical than a theoretical paper. And looking at Monte-Carlo and model calibration that I'll explain also later, then I'll do the conclusion. Yes, commodity derivatives serves a very important in helping us to manage the volatility of the commodity price. What is a derivative? A derivative is a financial instrument whose value is derived from another financial asset, or what you call the underlying. And derivatives are used for mitigating risk. And the volatility is actually a measure of uncertainty of the return of a particular asset. And that is the volatility. And apart from hedgers, the hedgers are the ones that are trying to mitigate or to reduce the risk. So those are the hedgers, market participants that are trying to minimize or to reduce the risk are called the hedgers. The volatility of the commodity price, also the keen interest to speculators. Speculators are those taking different market views because they probably want to lock in profit or to gain because of the market movement of the prices. However, the derivatives, they are most common, like forward contract is when you are entering a sell an asset at a particular date in the future, but you are obliged to make sure that you. There's also futures. Futures is the same as a forward, but the problem is that with futures is regulated by the exchange, and so there's minimize of credit risk. And then there is what we call the options. The options, you are not obliged. We give you the right, but not obligation to buy or sell and underline it. Now the underline, in this case, we call it like a future price of the crude oil prices. However, so now we want to manage the volatility, but however, recently, there's an observation that this volatility is rough. Rough means that normally all the mathematical finance models, they're based on the driving process, which is the Brownian motion, which is a continuous time stochastic process that increments are independent and stational, and also increments are normally distributed. But in actually empirical studies show that this volatility is rough, meaning the trajectory of this volatility is less regular than for a Brownian motion. That means a Brownian motion is incapable of being able to model this volatility. I'm going to give you an empirical evidence from during the global financial crisis that you see this is the realized volatility computed from the higher frequency data for the year from end of 2006 to end of 2010. And you see that the trajectory of this realized volatility is a bit more rough compared to the trajectory of the Brownian motion, which is indicated in the blue. And if you simulate the fractional Brownian motion, which is more rough, and the fractional Brownian motion, it will also come to later, to lights later. So you see that this is a continuous path. Of course, you cannot be able to model this rough volatility with a Brownian motion. So instead, you have to use some more processes that are more rougher. So now in this case, we come up with a model in order to, a tractable model in order to capture this volatility, or options or derivatives on this volatility. I promise you, I'm going to keep the mathematics very simple for everybody to understand what you are doing. We fix the time horizon T, and we consider a filtered probability space where omega here is just a sample space, and this script A is just a collection of all events on this omega, and we have a filtration here, which means it's just a continuous sequence of informations, and we assume that filtration satisfies the usual condition, that means it contains the p-null set and is right and continuous filtration. And the P is just a probability that assigns probability to events as they happen. We introduce the V, the vector of VT for within our time horizon, then we call this vector to model the volatility. It's a generic stochastic volatility process modeling the uncertainty of the crude oil volatility. And then we denote F, small t is current time, derivative time is capital T, which depend on the volatility by F. And this is the price, the future price of the crude oil for derivative capital T for all maturity. And here it's a well-known that consequently the spot price at time T of the underlying crude oil is equal to the spot price is the same as the future price at the current day. Okay, also we know that the expected future price at maturity, they converge under a risk neutral measure, and then we can write the future price like this. And we assume that know also the difference between the probability. This is a real world probability measure, and this is a risk neutral probability measure for us to be able to price derivatives, and in which in this world, all the investors, they earn the same interest rate at the risk-free rate. And this is what we're going to use in order to discount cash flows and to price derivatives. And we always use conditional to expectation, this conditional expectation, condition on the filtration to know that event has happened or not, or to actually know that this is a martingale, super martingale, or sub martingale. Okay. So we let W to be a Brownian motion, which is adapted to the filtration. A Brownian motion is a process that starts from 0 independent stationary increments, where the increments are normally distributed with a mean of 0 and the variance of the difference in the t, dt, or maybe t minus s. And so we have W to denote the Brownian motion, and then we have also WV to denote the Brownian motion that are driving the volatility process. This is the Brownian motion that are driving the future price, and this is the Brownian motion that are driving the volatility process. And again, because the commodity future price process follow a driftless stochastic process, that means your stochastic process or the ethos formula doesn't have a drift term. That means that the future price are martingale under a risk neutral measure because they don't have a drift. So now we can write it like this. Then we consider the volatility process that follows a stochastic dynamic according to, say, Cox-Singer-Ross models of 1985, which means the volatility process is a mean reverting model or process, which means mu v is just the speed of mean reversion, while nu is actually the mean level. That means if the volatility goes up, it reverts back to the mean. And var epsilon, this one is just the volatility of the volatility. And we know because of this square root, the process doesn't reach 0. And this is the Brownian motion that are driving the volatility process. And so because you want to make sure that the future price can hedge the whole volatility process, we make sure that these are correlated so that we can write the quadratic variation in this form, where rho is actually the correlation between the volatility and the future prices. Okay, now we construct up our models because we have WV, which is a Brownian motion. All these processes are adapted to our filtration. Or they're all generated by the filtration. We have W and WV. These are two Brownian motions that are correlated. And how do you generate two correlated Brownian motion? You generate two independent Brownian motion, W and W star, and then now you write it like this. Or you can actually, because now you are in a multi-dimensional, you can use Cholesky decomposition, and then you take the lower triangle matrix of the Cholesky decomposition in this form. And now That means if your correlation is equal to 0, that means your future price cannot spend or cannot hedge out all the risk that are involved for volatility. Then we consider the hump structure of the volatility process, which is actually a product of a polynomial function and also an exponential function. This is a polynomial of order 1 to the power 1, and this is the exponential function, and this is how you write it, and then now you can able to model the hump-shaped volatility in this form. Now, I want to explain this. I explained that there are, basic derivatives, there are 3 of them, basic one, the future, forward, and options. The options are the one that gives you the right to buy or to sell and underline. Now, in this case, the underline is a future price, which depends on the volatility. To give you the right to buy an asset at capital T, which is the maturity time. And so the call is options now, because we're concerned with modeling of options. The option, there are 2 types of option. You have a call or you have a put option. The call is the one that gives you the right to buy at some time in the future. And the put is the one that allows or give you the right to sell at a particular future date, which you call the maturity. And we have also 2 types of options. One, you can view it like that. You have American stylized option, the one you can exercise anytime, meaning you can exercise anytime before maturity. And you also have the European type option that you can only be able to exercise or to close out your position only at maturity time. And in most cases, we are dealing with the European stylized option. But because of this commodity is American stylized, but we're going to discuss the methodology of being able to convert European stylized option, American stylized option into equivalent European stylized options. To price a derivative, because you're standing at time 0 and then you're looking into a future, you need to discount it back to today. And so this is the price of a call option on the futures, which means the K is your strike price. That means you are going to buy future price. You agree today that you're going to buy future price at K. Now at future date, if the price is, then this is what you call the payoff, because now you're discounting it back to today at a risk-free rate. That's how you discount it. You have 2 maturities. You have the maturity of the futures, and then you also have the maturity of the options. And also keep in mind, we are working with these formulas are based on the European stylized option. That means you can only be able to exercise that maturity. Also, you also have the modern option, but that is something that you can able to exercise only at a particular discrete time point. Okay, so this formula here, the Black-Scholes and Moulton models were the first one to be able to compute the closed form exact price for the call option on a stock, for instance, but that Black-Scholes was more on a call option on a warrant option for the stock in a company. Unlike in Black-Scholes and developments, so here we don't have closed form solutions. So one particular, you can resolve it to Monte-Carlo simulation in order to find this expectation. And again, this expectation is given under a risk-neutral measure to make sure that we are using the risk-neutral valuation to exclude the arbitrage opportunity away. So this can be computed using Monte-Carlo simulations, or you can actually use the Fourier-based method of fast Fourier transform, or either the cosine method or transform method. In order to do this, you have to transform this into logarithms, and then you find the characteristic function. And how to do this? You let x equal to the log of this, And then in this case, also, we assume that your interest rate is constant. If interest rate is constant, then you can just take this expectation outside of this one here outside. And then if you let X to be the log of the futures, then you can use Ito's lemma. Ito's lemma is actually an application of Taylor expansion, and then you can derive it in this form. And the dynamic is given in that. Then we come to what is called the rough fractional stochastic volatility model. Volatility models, or what we call the rough fractional stochastic volatility models, are models that are driven by a fractional Brownian motion. Instead of taking a Brownian motion as a driving process, you replace that with a fractional Brownian motion. A fractional Brownian motion is a self-similar process with stationary increments, but it's not, the increments are not independent. And this is how it's given. The Brownian motion is given as W, and it has a H here. The H is the one that gives you the characteristic of the process. H is normally called the Hurst parameter or the Hurst index. For those that are doing physics, and I'm sure you're familiar with this. And the fractional Brownian motion was introduced in 1963 by Monte-Carlo, which means the representation of a fractional Brownian motion can be given in equation 9. So if the Hurst parameter is closer to 0, then the trajectory of this Brownian motion, or this fractional Brownian motion, is rougher, like the picture that you have seen on the second slide. So now this is a representation that you're going to, instead of, say, driving the volatility process, this process here, by a Brownian motion, which is this, you replace that Brownian motion by a fractional Brownian motion. Okay. And now we have, this is the representation that you're going to use. The biggest drawback of using a fractional Brownian motion is that the resulting process is no longer Markovian and is not semi-martingale. That means you cannot use stochastic calculus to derive a characteristic function or the pricing equations, and then also meaning Markovian, meaning that your process now depends on the history, and that's not nice. Now, instead, this is a clever approach, probably. Instead of taking the volatility being driven by actually putting a fractional Brownian motion here, you convolve the integral. If you take a solution of the previous equation, this one here, you take a solution of this equation, then it's going to be Vt equal to V0 plus the integral of this whole thing. Now you convolve that integral with a kernel. This is a kernel I'm going to talk about. With a kernel, is gamma, and this where alpha has a relationship between alpha and the Hurst parameter that introduces the roughness. If your alpha is closer to 0, it's less than 1 in this case, the solution of this equation here produce paths that are less regular than a Brownian motion. That's what we call the rough stochastic volatility. And this becomes very popular in financial mathematics literature. And where alpha is given as H, your Hurst parameter, plus a half. And this actually gauge or the control the roughness in the volatility process. Okay, well, now we want to price the thing with these models, now we want to price derivatives, we go through characteristic function, or we can go through Monte-Carlo simulation. But for calibration purposes, we want to derive the characteristic functions, and so that you can speed up the calibration and also efficient. So now you denote X as a log of the future price, and then here you derive the characteristic function or the transform like this. But the thing that I told you, this model is no longer Markovian and is not semi-mathematical. The only way to do is to assume you take a sequence of Hawkes processes and find the limiting case of this sequence of Hawkes process and show that it converges to this characteristic function here. And this is the characteristic functions to use, you derive. And then from this characteristic function, then you can price derivatives using Fourier-based approach. Again, this H here is a fractional integral. It's a fractional integral like this one here, and this is also fractional derivatives. And this fractional integral and derivatives, they are given like this. This is like a fractional Riccati equation. It's no longer the ordinary Riccati equations that are common in mathematical finance, but it's a fractional Riccati equation that you have to solve. Meaning you cannot solve this by using the ordinary, maybe say ODE 4-5. You have to look at other numerical schemes. And this is given like this. And now you can price the derivatives. You can take the expectation for discounting out. And this is a zero coupon bond with maturity capital T. And the K is when you're pricing the put. And to find the call price, you can just simply use the put call parity. And I'll explain it later. And this is how you price using Fourier method. Okay, I hope we find so far. So in order to price a derivatives, of course, you need a risk-free rate, because in the data set that you have, we still have calls and put. So we can derive the interest rate from the put call parity, which is given like this. A put call parity, it just means that the present value of your strike plus your call must be equal to the present value of your call. If you take T to this side and then you take ln of that, the present value of the strike plus the call is equal to the put price plus the future. That's a put call parity. So now we came up with a model, pricing equations. How are we going to convince ourselves that this pricing model works? So we compare it to the Monte-Carlo simulations. So we pick up some arbitrary parameters from this paper, and then we price. We are using the 3-factor model because in order to be able to model this volatility, we need to take at least 3 factors. This is what's common in the literature. Then I'm not sure if this is clear because the data were just too much to. So here you have the strike price ranging from 70 up to 130, and then this is the classical model. That means classical means that the volatility process are driven by a Brownian motion. Sorry, not a fractional, but a Brownian motion. Then the rough, it means the volatility is driven by a fractional Brownian motion with different Hurst parameter. If the Hurst parameter is equal to 0.5, then definitely you need to recover the classical approach. And then, so what we did, we ran a Monte-Carlo simulation in which we parallelize a Monte-Carlo such that in one run, it can able to give you multiple prices. And also in our model, we computed in such a way that you can get multiple prices. And then, of course, if you see the pricing and the Monte-Carlos, they're almost close to each other. And with also, if you see the computational time for the CPU time taken, for the classical is pretty quick, but as you increase the roughness, because when the H index is 0.1, it becomes more rougher, and it also takes more computational. It's heavy. Computational is very expensive when you increase the roughness. But of course, this also just gives us a motivation that our computational scheme is properly, and then we can now go on to be able to price derivatives as well as to calibrate our models to market data. Okay, so this was this just a put option, it's just the same. And then now look at our data set that we have. We have a data set of 21 years, but in this case, we're only going to consider a period of 3 years. During the period that we take, it's just a snapshot of our data set. During the global financial crisis, because that was a time of higher volatility period, and we want to check whether our model can able to reproduce the volatility of this higher volatility period. Okay, so what we do, we have options on futures that are traded on this exchange from 30th of October 2006 to 20th of October in 2010. And now this option on this or crude oil options are generally American stylized options. That means they can be exercised anytime before maturity. But the pricing equation that we derive are only for European stylized options. So we need to use an approximation, which is called the Baron-Adès-Wiley approximation that convert European to American stylized or American stylized option to European, so we can use our pricing mechanism. So these are for this period, that's the snapshot. These are the future prices. And of course, you see that during the global financial crisis, the longer time for maturity, say 12, you see that there's some peculiar issues here around the 2009 during the global financial crisis. And then you can also see the volatility that hitting about 0.90% during the same period of. And so we take, so our, this is our data set. We have about, only for that period of 3 years, we have about 87,000 options that we need to calibrate for. It's a big data set. Actually, we have 21 years of data that we need to calibrate. And each particular day you have a code, you have like a surface that you have to fit. So each day for all 3 years, you're fitting a model. Maybe in each day you have about 80 to 120 options that you need to calibrate. Meaning calibration, I'll discuss that later, but this is the options. This is a minimum of the crude oil future. This is a 10 percentile and 90 percentile, and the maximum prices for all these call put options, as well as the implied volatility. So this is the implied volatility for this particular day when the Lehman Brothers bankrupt, when they declare that now they are definitely bankrupt. So calibration. So you have the market price, both calls and put with different strike on a particular day. So calibration means you want to tune your parameters of the model such that the model price, the Euclidean distance between your model price and the market price is minimal as possible. So it's like an optimization problem that you have to solve. So we have now to fit the model both to put and to call at the same time. This is how you do it. So on each particular day, you have a set of parameters for the parameters that you fit your market calls. You want to make sure that the distance, the Euclidean distance between your model price and the market price is as close as possible. And also for the put, this is the number of calls on that particular day, and this is the number of calls on that, on number of put, number of call. Then you minimize this. And to minimize this is an optimization problem that you have. That means you have to use some optimization techniques like global and local. But in this case, I prefer global because the solution, if you use a local optimization, then the solution might stack at some local points, and then the solution will just give this is the best solution. But indeed, that's not the global minimum. And then, so these are the computations. So we have this parameter. Since we have about n factor or 3 factors, so now in this case, we have 25 parameters, including the Hurst parameter that we need to calibrate. Every day, we calibrate 25 parameters for the next 1,000 days or 3 years, or for the next 21 days. Then we have to run this. It's a highly computational problem that we're doing here. We convert American stylized option into European, and the rough fractional, because now we have a rough fractional differential Riccati equation that we need to solve. We solve using this scheme that was proposed by my other co-authors, Coragaro, Grasseri, Martino, and Pages. I got an opportunity to meet them when I was visiting the University of Padova in Italy, and they introduced me to this methodology of solving the fractional Riccati equation. And from optimizations, and this is one of my areas that I like, is we use the adaptive simulated annealing, which is a global optimizer that's able to solve this problem. Okay, so these are the model parameters, but because for the 3 years, we have about more than 1,000 days. Every day we calibrate 21 or 25 parameters. So this one is just a descriptive statistics. We link with the mean of that. And of course, this is a classical model, so we don't have the Hurst parameter in this case because we assume that the model is driven by a Brownian motion. And here now we have the Hurst parameter. Of course, you can already see that if the Hurst parameter is between 0 and 0.5, now that is rough. With from it's saying the internet connections. I'm not sure if if you look at the classical model, the dispersion, and also the classical model, I mean the fractional stochastic model, then you see that the stability of the calibration is very much improved. Okay. Then, because every day we have a Hurst parameter that you calibrate, then you plot this time series of the implied Hurst parameter. Hurst parameter is the one that measures the roughness. Actually, from this figure, you can already see that the rough parameter itself is rough. You see, the Hurst parameter itself is rough. Then here you're comparing these two models. When you calibrate, you're comparing these two models between the classical one is the red one, and the rough is the, you can already see that the errors for the blue one is always smaller. That means it provides a best fit. model for all the end-up period. Look at the global financial crisis. The classical one is inadequate. It cannot be able to fit. So this is a great motivation of our model, that it can able to fit even during periods that of higher volatility. Okay, well now, when then you compute, you want to compute the mean of the errors. The errors is actually the difference between the market call and market model. And then you also compute your distance between your implied volatility and the market volatility, implied volatility accordingly. And here you're just computing the standard deviation in order to see it clear. So this is the mean and this is the sample standard deviation. Now this is the fit. Again, if you look at the standard deviation for this, it's very small for the rough, but I mean for the classical, you see that the standard deviation is higher. Already it's an implication, it's a model implication that the rough fractional stochastic model perform much better. And of course, even if you fix your Hurst parameter to be the average of the implied Hurst parameter from the option, already if you keep your Hurst parameter to be calibrated every day, it provides a best fit. Okay, so this is a classical model. You fit. Already see that during the global financial crisis, it can't fit your data. So this is 1 month. This is 3 months. Already you can already see that this. Oh, sorry. I think I'm so much excited, and and yeah. So already, even for the 12 months, you cannot able to fit properly. And then if we move now to the rough case, look, 1 month is almost like a perfect fit to the model. 2 months or 3 months, perfect, almost the model. And then the 6 months, only a few points, but almost. It mimics the market behaviors of this volatility. That is a good motivation. And now what we call the out of sample. So out of sample means if you calibrate your model today, can you use today's parameter to price option tomorrow? Then out of sample is actually better because then you use today's parameter to price option for tomorrow, and then you find the error between tomorrow's price and then the model price that are produced on that particular day. If your model produces a smaller out of sample error than your model in financial mathematics or quantitative finance, taken as the good model. And again here, look, the errors compared to the classical. Our model, fractional, rough, is outperforming the classical approach. So in here, we calibrate today, we price tomorrow, option. So that's 1 day out of sample. And then the next part here, 1 week, like we calibrate today, Monday, we let whatever happen from tomorrow to next Monday. Then again, we price option on the next Monday. And then again, you see that the errors. So the model perform much better, even out of sample. I'm not sure this is the end really. Did I skip some slides? Okay, well, just to say that this is, yeah, so now we came to the end of my talk. So we presented forward volatility models for the crude oil market. And this model is very highly tractable, computationally intensive. and to price European stylized options, we were able to find an approach of converting American stylized option into European, and the models can be computed for calibrations in a very efficient manner. And we find supporting evidence that even implied Hurst parameters from these options, they're even rough. And roughness is actually a property that was derived from higher frequency data, but of course, even without even using high frequency data, using the option market data, we find an empirical evidence of roughness. And this model, this model can now be applied in other markets or to price derivatives, say on interest rate derivatives, or potential for modeling, robust modeling of other fixed income market, as well as energy or renewable market. And our next project is actually to be able to model weather and climatic changes derivatives, and which also going to be based on rough volatility. Thank you. I think I would appreciate if there are comments or questions from the audience. Thank you very much for listening tonight.
Yeah, thank you very much for the very interesting talk. Thank you very much. Are there questions